Siku and Jema A. This is looking at ancient and modern tools of astronomy, and we're probably more interested in the modern tools, but let's go through what we've got here. So a few terms to fill in, and this is where we're really interested in things. We have something called the modern tools section, and from grade 8 you should recall the electromagnetic spectrum. In the electromagnetic spectrum in grade 8, what you focused on was this narrow band called visible light, the Roy G. Biv. But anything that's part of the electromagnetic spectrum, varying from radio waves all the way to gamma rays, these things all travel at the speed of light. But how they differ is in their wavelength and their energy. And what this is trying to show is as we go to the right, the wavelength gets shorter and shorter, things become more compressed, and they end up at higher frequency, and higher frequency corresponds to higher energy. And down here it gives you a comparison of these things. Well, it turns out a lot of the tools astronomers use, well, they'll have things called radio telescopes and microwave telescopes and X-ray telescopes. And those things are designed to detect different types of radiation. And it turns out the bigger the wavelength, the bigger the telescope has to be. So radio telescopes are going to be huge. So, friendly reminder what I just said. If you have a longer wavelength, that'll have a lower frequency, less energy. Shorter wavelength will have higher frequency, higher energy. So in the chart above, the longer wavelength radio waves on the left, and as you go to the right, you get the higher energy on the right, the X-rays and gamma rays. Not surprisingly, higher energy, more damaging. In grade 8, we talked about Roy G. Biv, R for red. So infrared, that's heat radiation. And infra means below, so it's below red in terms of energy. Ultra means above. So when we have ultraviolet, we're to the right of violet. And we know that ultraviolet radiation can be damaging, and that's why people will do things like wear sunscreen and protect themselves from UV rays. We've talked about the spectroscope already and given us the light print of stars. So that was an earlier set of notes about astronomy and come back in chemistry. And the spectroscope is hugely important to astronomers because from the light print we can identify elements in stars. We go to the back side. We look at radio telescopes. So here we're looking for the lowest energy, longest wavelengths of the electromagnetic spectrum. It talks about what they can pass through. This is nice. It can pass through clouds and rain, so the atmospheric conditions aren't going to have a huge impact on them. Talks about a parabolic shape, so not a circular shape. You hopefully learn about parabolas in math. And in fact, the radio telescopes have to be so big because of long wavelength, they're set up in arrays. And you should have seen some radio telescopes or arrays, either in videos you've seen or that you'll see this week. And it says one of the things they do is they try to detect evidence if there is extraterrestrial life out there. Microwave tells us about the temperature of objects. Infrared, not surprisingly, tells us about the heat. You might remember we have things called infrared goggles, night vision. Optical telescopes are traditional ones and still used today. And they'll involve lenses, and the more complicated ones involve lenses and mirrors. And the bigger they are, the more precision they have in terms of viewing things. Unfortunately, optical telescopes are affected by the atmosphere. And so if you set up your observatory in a cloudy place or in a place where there's lots of daylight and things, that's a problem. So typically optical telescopes here, they try to set them up on mountains, places near the equator where you're going to have a good chunk of darkness. You'll have close to 12 hours darkness year-round. And of course, the Hubble telescope solved the atmosphere problem by being launched into space and operating above the atmosphere, so it gives the best pictures in terms of using light. So here's where it talks about observatories. We want them on mountains, we want to be above the clouds, we'd like it to be dry, so more desert-like. And so there are a lot of observatories in South America near the equator. And we are getting there. Ultraviolet telescopes. So they're detecting ultraviolet rays. And it says, hey, since newly formed stars give off a lot of ultraviolet radiation, then if you're using a UV telescope, you are going after those new stars. X-ray telescopes, very useful in detecting things like black holes, neutron stars, binary stars, things that are giving off X-rays. And so if you're getting information here on Earth in the form of X-rays, you go, whoa, you can track back in that direction and know that you might have a black hole or a neutron star. Gamma rays, very short wavelength, highly energetic, damaging to humans. Don't let anyone hit you with a gamma ray gun. And it talks about how the gamma rays can actually pass through the telescopes and have to be detected in a different way by seeing how they push electrons around. And the Hubble I've already mentioned, where it's orbiting at 500 kilometers above the atmosphere and giving those crystal clear images. So that's a snapshot of the different types of radiation and the different types of radiation telescopes that are used to learn about the universe.